Okay, on to an example. So we've been talking about hydrostatic pressure, and I want to give you an example of how we could actually use that to do something practical. So what do we have here? Well, we're using a basic barometer. It's something that measures pressure. We're going to use it to measure the height of a building, and you can actually do this. So what we find is that barometric readings at the top and the bottom of the building are 675 and 690 millimeters of mercury. That's a unit of pressure. It says use that to determine the height of the building. It says take the densities of air to be 1.18 kilogram per meter cubed and mercury to be 13,600 kilograms per meter cubed. Okay, so how do we use that millimeter mercury thing in the first place? Well, what we're going to do is we're going to use it to get a pressure at the top and a pressure at the bottom. And the second thing we're going to assume is that our air density just isn't changing as we go up the building. If we do, we have to do more calculations, a little bit harder, but honestly, even though it does change slightly, it's fairly negligible. Okay, so here's our building, we're just drawing it, and now we're going to calculate the pressure at the bottom and the pressure at the top using our barometer. So the pressure at the top, we're just measuring it using hydrostatic pressure in our barometer. So we have mercury, and we have 675 millimeters. I convert that to meters because everything else is in meters. My gravity is in meters per second squared. My density is in meters cubed. I need to make sure it's all in meters. That gives me 90,050 newtons per meter squared. Where in the world did Newton come from? That is a kilogram meter per second squared. So these three units right here turned into newtons. I do the same thing at the bottom. So density of mercury times gravity times the height of the mercury. And that gives me 92,060 newtons per meter squared. And just so you know, this is technically what's called a Pascal. A Newton per meter squared is a Pascal. So I have this difference in pressure from the top to the bottom. Why do I have this difference in pressure? Well, the reason I have this difference in pressure is because of hydrostatic pressure of air. I have this pressure of air that is in between here, and that's why I have a difference in pressure between the top and the bottom. And I can figure out actually how big that air must be to cause the difference in pressure. So I write it out. I simply say that my pressure of air, right here, is going to be equal to the difference in pressure from the top to the bottom. As I note, since there's more pressure on the bottom, I put it first just so I have a positive number. I then solve for it. I know what the density of air is and gravity is, so I can divide that out. And I get that the building must be 172.5 meters tall. Now, you can actually do this yourself. How do you do it? Well, you would use what's probably called a manometer instead, because you probably don't have a barometer. And you can actually measure the height of tall buildings doing this. So, the way it works is the following. As a note, this is an extra credit assignment I actually have in my classes, so definitely a fun one to do. What you do is you take a piece of wood. It doesn't have to be wood, it just needs to be stiff. You get some flexible tubing, and you put that flexible tubing onto the piece of wood in the shape of a U. You then need to fill that with some water. After you've done that, you put a cork in one side, you seal it in some way so that it can't have any airflow out of that side. That's sealed. Oop. Then you make some marks on both sides to tell how high or low the water is. When you go up a building, what you're going to see is that the water on one side is going to go up and the water on the other side is going to go down. And that difference right there, that height difference, is actually the difference in pressure. And so what you'll see then is rho water times gravity times the height difference of water is equal to density of air times gravity times the height of the building. Whoa! There we are. So you can use this little homemade manometer to actually measure the height of buildings. Is it super accurate? It depends on how good you are at reading the difference in height, how well you sealed it. There's other things that are going on here. But it can be done. So try it out. Let me know how it goes in the comments. So thank you all so much, and I will see you all next time. Bye-bye.